Now, the next LSA is type 4, but type 4 is so incredibly complex that I cannot possibly explain it, so I'm just going to skip it. So type 5 is the external LSAs. Let me explain that. So type 5s here, let's say that we have our network, the one that we have been using to illustrate the previous examples as well. So I have R1, R2, R3, and then R4, and this here are our ABRs. So let's say that here I have area 12, area 0, and here I have area 34. Now, when R1 here has some external network, so let's say that it is also running RIP, and it's configured to actually redistribute these routes into OSPF, it is going to do that by injecting type 5 LSAs. Now, type 5 are external LSAs, so type 5 contains redistributed routes, and this act of redistribution is one of the things that will actually make R1 be an ASBR, or the Autonomous System Border Router. So, filling out this table here, the origin of the external ASA is going to be the ASBRs, and the data contained will be redistributed external routes. What is the flooding scope of this LSA? Well, there are two possible options here. One is that the flooding scope is actually an area, and that then this redistribution happens actually hop by hop, just like it did with type 3 LSA, so that we have one here and then another one here that stops here, but this is not how it works. So this is not how type 5s work. The way type 5s work is actually that the flooding scope of type 5 LSA is the entire domain. So this type 5 generated by R1 here is going to be flooded in the entire domain. So here on R2, we are going to have the information that let's say that we have network N here, that network N is reachable through R1. Now, R2 knows who R1 is, but this same information will be visible on R3. Now, R3 here has a problem. Who is R1? Because R1 here sits in area 12, and R3 is in area 0 and in area 34. Now, the same problem exists on R4. R4 doesn't know who R1 is. Why? Because it's in a totally different area than R4. So we need to provide some additional piece of information. We need to provide some little more help to our routers R3 and R4 in order to be able to reach this network N. And this is where type 4 LSA comes into play. So when I said it is incredibly complex and I cannot possibly explain it, at that point in time that was true, because on its own type 4 is completely meaningless, because it works in conjunction with type 5 to solve this problem of multi-area reachability for external routes. So the way this works is, first let's look at what's the name of this LSA. iOS calls it ASBR Summary LSA. It is generated by ABR routers, and the data contained are the router ID of ASBRs. The flooding scope of external LSA is the entire domain, but the flooding scope of type 4 LSA is actually an area. So the way that works is here on R2, R2 is going to generate type 4 LSA, basically telling router R3 or routers in area 0 that router R1 is actually reachable through R2. R3 here is going to tell routers in area, so let me be consistent with colors at least. here because I used green there. So here R2 is going to say that R1 is reachable through R2, and this information stops at this point. R3 is going to generate its own information here that's going to say that R1 is actually reachable through R3. Now, this information is now available here because we have information that R1 is reachable through R3, so we can actually compute this route here in conjunction with this information here. The same situation we have on R3, that R1 is reachable through R2. We know who R2 is, so we can actually compute this in conjunction with this information, so we are actually good. So type 4 and type 5 work together. Now, there are two questions here that I may need to answer. One question is, why on earth did they do it this way? And so what's the point of this all? And the second is, what triggers R2 to actually generate type 4 LSA? Let's first answer that first question I had. To illustrate that, I'm going to have a slightly different network. Again, it's going to be just 4 routers, just slightly different topology. So this is the topology that I'm going to have now. So let's say that this here is area 1, 2, 3, and these are routers 1, 2, and 3. And let's say that this here is area 0, and let's say that this is a router 4. All links in this network are of equal cost. And let's say that R1 here has some external network N that is being injected into our domain. So let's say that this network N, now, so I'm first going to explain how it doesn't work. And I think it will become clear why it's not the way it works. So let's say that the behavior of type 5 LSA was exactly the same as the behavior of type 3 LSA. So when this network was advertised, routers R2 and R3 would receive this information, which would stop at them. Then R2 would generate its own LSA here, and R3 would generate its own LSA. So basically, what am I going to end up having here are 2 times LSAs that originally existed. Now, if for example this was 5,000 LSAs, what am I going to end up here is 10,000 LSAs. I'm going to have 5,000 green ones, and I'm going to have 5,000 blue ones in my OSPF database. So I'm going to be multiplying information that I have in the database here. So this is not how it works. So if this is not the way it works, how does it then work? So let's examine that. So I'm going to delete all this stuff here that is unnecessary. So let's say that R1 here is injecting 5,000 LSAs. So these 5,000 LSAs are going to be sent to 2 and 3. Now remember that before we actually send out the actual LSAs, R2 and R3 are going to send the information that these LSAs exist. And interestingly enough, these are going to be same LSAs. So R2 is going to be saying, hey, I have these 5,000, and R3 is going to be saying, hey, I have these 5,000. So basically what R4 is going to do is either going to request all 5,000 from one of them, or maybe 1,000 from this one, 4,000 from this one, or any way it gets, what's going to end up in the routing, in the database, are going to be 5,000 LSAs. So somehow this information is going to get in here, and this information is going to get in here. So I'm going to have 5,000 original LSAs somehow entered in my database here. It doesn't matter from which one of these 2 routers I learned them from. Then R2 here is actually going to say that R1 is reachable through R2. So here I'm going to have +1, and R3 here is going to say that R1 is reachable through R3, so I'm going to have +1. So the total number of LSAs here is going to be 5002, and based on these 5002, I can actually compute two equal cost routes for both of these networks. So what actually ends up in the routing table are 10,000 routes in the routing table based on only 5002 LSAs. Now, to illustrate this even further, imagine that our network actually looked like this. So if this was the case, I would still have 5000 type 5 LSAs, and I would have 4 type 4s. So I would have 5004 LSAs in the database, but I might actually have 20,000 routes in my routing table. You see how the number of ABRs here does not multiply the number of LSAs in the database. Now, if I used this approach here with 4 ABRs, I would actually have 20,000 LSAs for 20,000 routes. So I would be consuming much more memory in my databases. So that's the reason why type 4 LSAs propagate the way they propagate and not some other way. So where is the here is the that diagram. Now, another question that remains to be answered is what actually triggers a router to generate the LSA? But I believe that I may have a question coming up. The question here was, if I have these 4 routers, R1, R2, R3, and R4, the question was, when I have this LSA that goes end-to-end, so this is type 5, and type 4 is generated here, will type 3 actually generate a different type 4 at this point? Yes, the answer is yes. This type 4 is not the same as this one here. So let's call this type 4 from 2, and this is type 4 from 3. So type 4 from 2 is not the same as type 4 from 3. They are going to be very different. The origin here, the originating router will be R3. The content will be router ID of R1. So this is what going to be the ID. Sorry, the LSA ID will be R1, and the cost would be R3's cost to R1, and the information here would be that the origin is R2, the LSA ID will be R1, because this is what we are talking about. We are talking about R1's router ID, and the cost would be R2's cost to R1. So these two are not the same. Yes, the type 4 LSA will be regenerated in a very similar fashion in which type 3 LSA is regenerated. The question that I asked before this one was, what triggers the actual generation of the LSA? So if we take a look at our 4 routers, R1, R2, R3, and R4, so different databases here, so let's draw borders. So this is area 12, this is area 0, and this is area 34. Now, we know that this external LSA is going to go end-to-end. So this is type 5. Now, the important thing to know is that the presence of this type 5 does not trigger generation of type 4 LSA. So I'm going to write that down in red. Type 5 does not trigger generation there are 2 triggers that generate type 4 LSAs. Those are router claiming spelling mistake, sorry about that. So if the router claims to be an ASBR, an ABR will trust it about it. And the second is type 4 LSA. What's wrong with me today? Type 4 LSA will trigger regeneration. Let me explain that. So here, just below this table, I actually have another table that I have somewhat hidden from you. So I'm going to bring it up now so that you can see it. Inside type 1 LSA, there are a couple of bits that don't have any particular name, so I call them VBE bits. They stand for Virtual Link Endpoint, which is not something that we care about right now. The B bit, which is going to be set on all the routers that perform border functions, and there is this E bit, or the edge bit. So when the router claims to be an ASBR, it is actually going to be R1 here sending an information in type 1 LSA with the E bit set to 1. Now, when E bit is set to 1, basically R1 is telling R2, I am an ASBR. Now, when R2 receives this information, it is based on this information here going to generate a type 4 LSA that will travel to R3. Now, R3 here, of course, doesn't see this information here, but it does have this information. So this is this second trigger. So this presence of type 4 LSA will cause our R3 here to actually regenerate type 4 and send it into the area 34. Now, this is very important because if this wasn't the case, remember that we could have 5,000 of these type 5 LSAs. Which one of these type 1000 actually triggers the generation of type 4? Well, it's none of them. It's not the first one, it's not the last one, it's not the 15th one. It's actually an updated type 1 information. And that is very important because you can have a situation that router is configured for, let's say, redistribution, R1, but it's not actually redistributing any routes. If you take a look at R2, you will actually see that R2 is generating type 4 LSA for R1, even though there are no external routes. Why? Because R1 is actually claiming to be an ASBR. So it's information in type 1 LSA that triggers the generation of type 4 LSA on R2. Those were type 4 and type 5 LSAs. Now, there is one LSA type, which is called multicast OSPF, which is not actually supported by iOS. So that's what I'm going to add here. I'm just going to say that this LSA is not actually supported. I'm going to write this down. So you're not going to see this in OSPF. Now, you can still be asked the question about type 6 LSA, and if that's the case, what you have to remember is ignore LSA MOSPF. I believe that's the command. I might be wrong, but this is in a router OSPF. This is pretty much the only thing that you can do about type 6 LSAs. Just gracefully ignore it. Type 7 LSA, and again, here is where we are hitting that chicken and the egg situation. I have to talk now about the NSSA external routes, but I haven't talked about what the different area types are, but I'm going to come to that in just a couple of minutes. But for now, let's just take a look at what this does. So NSSA external LSA, let me scroll this up so that you can actually see it. So NSSA external is generated by ASBRs in NSSA area. The content of the data inside this LSA are redistributed external routes. But what is the flooding scope of this LSA? Well, let's take a look. So if we take a look at our network again, so again I have R1, R2, R3, and then R4. Let's say that here we are redistributing some network N, and this is now actually NSSA area. This type 7 LSA is going to reach this point here. So this is going to be type 7. Now, based on information from this type 7 LSA, R2 is going to inject type 5 LSA. So this is going to be type 5 LSA. In area 0, there will be no type 4, but in area 34, there will be type 4 for this, and it's going to be that R2 is reachable via R3. Because at this point here, R1 does not figure, it does not exist. Information about R1 was lost at this point when information from this LSA was actually used to generate this new type 5 LSA here. So this is how NSSA information is propagated outside of the NSSA area. Which brings me to an incredibly important concept. And for that, I'm going to use again that other network that I had. So let's say that we have R1, R2, R3, and R4. These are the connections, and they're all equal cost. And this is the area border. So there is no connection between R2 and R3. This is just a border between them. Okay? Now, this is, let's say, area 123 NSSA, and let's say that this here is area 0. And let's say that our R1 here is injecting 5,000 routes inside. So these are going to arrive to R2 and R3 and stop here. So these are type 7s. So what's going to happen here is that R2 is going to generate its own 5,000 type 5s, and R3 is going to generate its own 5,000 type 5s, which means that on this router here, I'm going to end up with that old problem of 10,000 LSAs. So let me reassure you, this is not how it works. Because if this is the way it worked, we would have a big problem. The way it actually works, and now it's the cleanup time, is that these two type 7s actually do arrive to these two routers. But then these two routers here are going to have a sort of an election of who translated. Let's say election of translating ABR. Now, the election is very, very simple. Highest router ID wins. Now, keep in mind that these two are not directly connected. So how do they know about each other? Well, very simple. Because they are both in area 123 and both in area 0, and their databases are identical. They of course know that they are both in area 123 and that they are both in area 0. And R3 is going to look, what is the router ID of R2? What is my own router ID? If mine is higher, I will be the translating ABR. R2 does the same thing, and let's say that they agree that it will be R3 who is the translating ABR. So what's going to happen here is R3 is actually going to inject 5,000 type 5 LSAs. So what I'm going to end up having here are the 5,000 LSAs in the database. But the funny thing that's going to happen next is that based on these 5,000 LSAs, what I'm going to end up having, if all links are equal cost, are 10,000 routes in the routing table. But how is that possible if the origin was R3? Well, this is where an incredibly important concept of forward address comes into play.